In the last few videos, we've been talking about this hyperfine interaction, which we showed was the Hamiltonian for that perturbation could be written as A over h bar squared, the electron spin operator dotted with the nuclear spin operator. And this arose from essentially the interactions between the magnetic moments of the proton in hydrogen and the electron in hydrogen. And we were looking essentially in the last few videos at just that ground state of hydrogen, which, when we include the spin degrees of freedom, is degenerate in our first look at the hydrogen. Looking at that ground state wave function, it's spin degenerate. And then we looked at how this Hamiltonian affects that. And we looked at perturbation theory, and which says diagonalize the perturbation matrix in the degenerate subspace. And so we wrote that matrix in terms of what we called the uncoupled bases, right? So just those four different combinations of the electron and the nuclear spin. So written in terms of ms and mi, where it's spin up or spin down on the electron and spin up or spin down on the proton. Right, and after we diagonalized this to see what the actual energy eigenstates were after the perturbation, we realized that these polarized states were the same, and the four energy eigenstates could be written like this. There was a polarized state where they were both spin up. There was a combination or sort of a superposition of the two unpolarized states, another polarized state where they were both spin down, and then an anti-symmetric combination of the two unpolarized spin states. And that these were the eigenstates that we found when we diagonalized this perturbation Hamiltonian in the degenerate subspace. And we called these triplet states because all of these states went up together and they had an energy shift where they went up A over 4 in energy, and this was what we call their singlet state because it went down off by itself. It had an energy that was shifted down 3/4 of A. And we solved that. That was sort of what the perturbation did to our degenerate and we saw that was what the perturbation did to our states and our energies of our ground state in hydrogen. And then we started, last video we talked about, we did a bunch of work diagonalizing the matrix using this uncoupled bases. Why didn't we just use this bases from the start, right? That perturbation matrix is already diagonal if we're using these as our basis vectors. And then we could have saved ourselves a lot of work if we had some insight and said, all right, well, let's use what we call now the coupled basis. That we could have just figured out these energy shifts by inspection. The Hamiltonian would have had eigenvalues across the diagonal, and we could have immediately just seen that these were the energy shifts due to that perturbation. And what we realized was that the thing that sort of made or defined what our sort of good bases was what quantities were conserved, right? And we realized that in this this perturbation was essentially the interaction between two magnetic moments which exert a torque on each other. So the individual angular momentum, or the individual magnetic moments, which are kind of related to these individual magnetic quantum numbers, those aren't conserved. So it's not really a good set of quantum numbers or a good set of basis states to describe this system because they're going to be changing. They're not conserved. Whereas the coupled bases, these coupled states can be labeled by a sort of a total angular momentum and a magnetic quantum number for that total angular momentum. And because the torques in our system that are exerted on these two spins are internal torques, there's no external torque, these numbers are going to be conserved. And those were the basis states we want to use. what we saw was the excuse me. So what we saw was that this coupled bases, this MJM, we could write that in terms of our uncoupled bases, in terms of the spins on the electron and the nuclear spin, and we had essentially our J equals 1 and MJ equals 1 state was our polarized spin state. Our J equals 1, MJ equals 0 was that symmetric combination of the unpolarized states. Erase that. Of the unpolarized states. The -1 state was the polarized spin down state, and then we had our singlet state where the J equals 0, MJ equals 0 state was the anti-symmetric combination of our spin, unpolarized spin states. So we had figured out, we'd related our coupled bases to our uncoupled bases and sorted through that and kind of said, okay, why we should have just used this from the get-go. Then our perturbation matrix is diagonal in that basis, and we could have figured out the energy shifts just by inspection. Today what we're going to do is, we're going to look at sort of this whole process in general, right? What we were really doing here, we were just taking two angular momenta in our system, the spin of the electron, spin of the proton, adding it together to get a total coupled angular momentum bases. Today, we're going to look at the process of how to add angular momentum together, and this is going to be the same sort of process that we would use, if we want to take, let's just take for the not just the n equals 1 state, but if we wanted to add orbital and spin angular momentum of an electron and include both of those together or things like that. We're gonna use sort of what we're gonna cover today to add those angular momenta. So let's go through the example we just sort of did and see in general how we would add for the addition of two spin 1/2 systems. In this case, we had the nuclear and the electron and the nuclear spins, both spin 1/2, and we were adding them together to get our total angular momentum. The book calls S plus I, and this is what we're trying to sort out, right? What we can do is we can look at what we generally are going to do is if all these spins or all these angular momentum are aligned, we're in what we can call a stretched state, and that's going to define an eigenstate for both of these. In this spin 1/2 and 1/2 system, that's the polarized spin state was equal to the 1 state in the hyperfine example we were doing, and we call this sort of the stretched state. It's the it's got the largest angular momentum in both bases. It's going to be an eigenvalue, and we can take that and use that to sort of generate the rest of our states. And the way we generate them is, we go to the top state in our manifold of if you remember when we're looking at general angular momentum, it's going to have some total angular momentum and some magnetic momentum quantum number. And for any given, angular momentum quantum number, it defines a manifold of states going from -J all the way up to +J. That manifold of states, if we start at the top, we could then use a lowering operator to walk through all these states and figure out every state in that manifold. And that's essentially what we're going to do with here. We identify the start state, the initial state, and we're going to look at the lowering operator, which is just, in terms of the individual angular momentum operators, is just the sum of those two lowering operators. And we're going to take that and operate on our stretched state to get the next state down in this basis, right? So for this spin 1/2 system, the two spin 1/2 system that we have F minus operating on 1,1 is going to be equal to F, the lowering operator, operating on our, I'm going to write it as 1/2, 1/2, where this is our MS, MI uncoupled bases. And this is also equal to, we're just going to use this, S minus plus I minus, operating on that 1/2 basis state. And so all we really need to do is know how these lowering operators work, right? So we have the F minus operating on those, where again, this is the F, M quantum numbers, that coupled bases. That equals, the eigenvalue equation is H bar F plus 1 minus M minus 1. And it gives us the state 1. I should have written this in terms of general quantum numbers. So let's do that. Is that in terms of F and M, this gives us F and M minus 1. So that's sort of the action of the lowering operator on one of these coupled eigenstates. In terms of, if we have this SI operator, for example, or S minus operator operating on a particle that is S and MS, this is going to be the same sort of thing, where we have H bar over S plus 1 minus MS minus 1. And it gives us MS minus 1. It just goes down that manifold. Now, keep in mind this spin 1/2 system has S equal to 1/2, and we're looking at the MS quantum number here. So we're going to have to keep that in track. But anyway, so what does this mean? Well, if we do it for these values, on the left I have this operator gives us H bar square root of, well, it's a spin 1 state, so that's 1 times 1 plus 1, so that gives us 2. And then this M times M minus 1. Well, if M is 1, which it is here, that's just going to be 0, so that's 2 minus 0. And it gives us 1, and then 1 minus 1 gives us 0. So that's the left-hand side of our equation. We have root 2 H bar 1, 0. And on the right side, we have, well, what's S minus operating on this state here? Well, it's going to be H bar. So let me write this out in full. This is S minus operating on 1/2 plus I minus operating on 1/2. This is going to be H bar square root. Well, we have S is 1/2, so we have 3 halves times 1/2 gives us 3/4. And then it's minus, and we have 1/2 minus 1, so that's negative 1/2 times minus 1/2, so that's going to be plus 1/4. And that's going to give us, we're going to go down an integer number, so that becomes negative 1/2. And then for the I term, it's going to be the same thing, it's just operating on this, so we have H bar square root 3/4 plus 1/4, 1/2 minus 1/2. Right, so this whole thing ends up being, well, this is just 1, so we have H bar times negative 1/2 plus 1/2 negative 1/2. Right, so we have this side, that side, h's cancel. We know that 1, 0 state is just going to be 1 over root 2 times the 2 spin up and spin down plus spin down and spin up states. So written in terms of the just plus minus kets that we might be more familiar with, that's just our plus minus plus minus plus states. So you can see we do that. We just start with our stretch state, use the lowering operators, go down to our next one. We do this again. We apply F minus again, and we're going to get our 1 minus 1 state. And naturally, we're going to see it's the same thing we expected. We will end up getting that as our state. So we've figured out just by using these lowering operators, these ladder operators, three of our basis states, right? Starting with, we have the stretch state that we kind of started with, and then we got these other two states. There are four states though, so we need the fourth basis states. This is a four-dimensional subspace here. So how do we get that? Well, to get the fourth state, it's in a different manifold, right? It's not in that F equals 1 manifold. So what we end up using is orthogonality to get to the different things. We know that this 1, 0 state is going to be orthogonal to that 0, 0 state in the other thing. So if these are orthogonal, we have 1, 0, 0, 0 has to be equal to 0. So we can take that and say, all right, well, I know this 1, 0 state, so I can just say, well, 1 over root 2 times 1 half plus, 1 half minus 1 half, 1 half minus 1 half, 1 half, getting tongue-tied. The spin up, spin down plus spin down, spin up states. If I take the inner product of that with this 0, 0 state, which I can write as any linear combination of those spin 1 half states, 1 half plus B 1 half minus 1 half plus C minus 1 half plus 1 half plus D minus 1 half minus 1 half, right? Because these uncoupled states are basis states, so I can write any vector in terms of them. I can do that and then take this inner product, and what I'm going to get is that only these terms come out to be non-zero because I know those are orthogonal, and I get 1 over root 2 times B plus 1 over root 2 times C is equal to 0, or B is equal to negative C, or my state, and with normalizing, I get that 1 over root 2 again, or normalizing, I get my 0, 0 state is going to be equal to 1 over root 2, B is just going to be spin up 1 half minus 1 half, and then the minus C comes in minus 1 half, right? And that gives me the fourth state. Looking at this orthogonality condition gives me the fourth state, and I've sorted out the coupled and the total angular momentum bases for adding those two spin 1 half states, and I got the same ones we got previously. So summarizing this sort of conceptually is what we did was we started with our stretched state, right? That polarized maximum sort of angular momentum state where I had F is equal to S plus I, which is, 1 is equal to 1 half plus 1 half. And then I said my F and M are equal. I'm starting at the top state in that manifold, and this is what I get. And then I used my lowering operator, F minus, to get to my 1, 0 state. And then I used my lowering operator again to get to my 1, negative 1 state. And that gave me all the states in this F manifold. And then what I used is orthogonality to get to the 0, 0 state over here. And that sort of defined, or is how I figured out all the four states in this coupled bases, or in the total angular momentum bases. So, excuse me, mapping this to sort of any general system. Let's say we have two systems we want to, with angular momentum, and we want to combine them into one coupled system. We're going to have the angular momentum of the first system plus the angular momentum of the second system is going to equal our total angular momentum for our combined system. The sort of coupled bases the coupled bases is going to have quantum numbers J1, J2, J, the total angular momentum for the system, and that magnetic quantum number for that system. And the uncoupled bases is going to have J1, J2, M1, and M2, right? So in this case, these quantum numbers sort of come from the operators J1 squared, J2 squared. Those are common to both, right? For the spin 1/2, the 2 spin 1/2 example we just did, the intrinsic spin of the electron doesn't change, neither does the proton change. Their orientations and everything might, but those quantum numbers, the total angular momentum of those two systems, don't, or the magnitude of those total angular momentum don't change for those systems, so that they're both going to have the same quantum numbers. These M1 and M2 quantum numbers relate to the J1Z and the J2Z quantum numbers, whereas this J quantum number here is related to the total angular momentum squared operator, and it sort of relates to the magnitude of the total angular momentum, and that M quantum number is related to the Z component of that. And we're going to sort of want to, what we're really doing is, well, we know the systems, we know the possible states with the individual systems, and we want to be able to relate them to the coupled total system, and we want to know how do we add those angular momenta to get that, right? So in really quick, in that spin 1/2 system that we just had, we have our coupled system J1, J2, J, and M. In terms of our uncoupled bases J2, M1, M2, well, since the J1 and J2, the individual systems are kind of implied and they're not going to change, we can write this just in terms of the two quantum numbers Jm. We're going to leave these ones here in our uncoupled bases, so just to keep track of things. But in that spin 1/2 system, we had the 1-1 state was equal to the 1/2, 1/2, 1/2, 1/2 is how we would have written it in this general sort of form. And then we can go down and do the other ones. I'll just do the 1-0 state was 1/√2, 1/2, 1/2, 1/2, minus 1/2, plus 1/2, 1/2, minus 1/2, 1/2. And I've written these enough times in this video and the previous videos that you can get through them. This is just sort of a new notation that maps what we've just done to a more general case sort of notation. And the process that we use to get these in general is we start with this stretched state, right? So we know that the total angular momentum has a maximum value of J1 plus J2, right? If both magnitudes of the individual systems are sort of aligned in the same way, they add to have the maximum possible total angular momentum. And they can go down to all the way down to, in integer steps, J1 plus J2 minus 1, all the way down to, well, consider them anti-aligned, those angular momentum. You're going to have the total angular momentum be the difference between those two angular momentum, right? The absolute value of those is the smallest it can be. Is if they're sort of anti-aligned and one was still bigger than the other, that's the smallest they can be. So that sort of defines the different J values we have. For each one of these total angular momentum quantum numbers, that defines an M manifold that can go from J, negative J rather, to in integer steps all the way up to positive J. And the process that we do to sort of sort all these out is we start with that stretched state, which is the J equal to J1 plus J2, and the M equal to J1 plus J2 state. We take that state and we apply that ladder operator, that lowering ladder operator to it, and that gives us our J1 plus J2 and J1 plus J2 minus 1 state, right? We've gone one state down in that J manifold, and then we go and apply that ladder operator again, and it gives us the J1 plus J2. J1 plus J2 minus 2 now, state, and we just keep going down that manifold, that J manifold of M states, and we'll just keep going and lowering operator until we get to this bottom possible value where we have the J1 plus J2 and J, that value being the difference, J1 minus J2 absolute value. And we get to that bottom state. And then we've got that whole manifold defined. We're going to use that orthogonality condition to get to that next set of J1 plus J2 minus 1, the next J value in our system. And it's going to have the J1 plus J, sorry, 2. Let's move over here. J1 plus J2 minus 1 state. And then, again, use J minus to get through that manifold until we get to the bottom. And if there's more, then we use orthogonality again to get to that state, and so on and so forth. So we start with the stretch state here, lowering operator, fill that manifold, orthogonality to get to the next manifold, lowering operator to get all the states in that, orthogonality, and you just keep going until you've got through all those different angular momentum manifolds and sort of figured out what all of those states are. Excuse me, in general, you can sort of imagine this can get pretty tedious, figuring out the action of all of these operators and the orthogonality. If you have a large angular momentum spin system, or a large angular, two systems with decent sized angular momentum, this can be a really tedious process. So just to sort of map out and see what we're working with, let's look at two spin one particle system. So we have two particles, each with spin 1. And let's walk through this process a little bit. So if we have two spin 1 particles, that means that our J1 is equal to 1 and J2 is equal to 1. So our stretch state is going to be J, the total angular momentum, equal to 1 plus 1. So that's 2 and 2. And it's going to be equal to the state, J1 is equal to 1, J2 is equal to 1, M1 is equal to 1, and M2 is also equal to 1. So that is our stretched state. And we apply our lowering operator, J minus, to that to figure out what our next state is. So J minus, operating on 2, 2, it gives us, if you recall, just to remember what the action of this operator is on a JM state, is equal to H bar square root J plus 1 minus M minus 1, and it gives us the J M minus 1 state, right? So on this case, in this case, that gives us H bar square root, 2, that's 3 times 2, so that's 6. And then minus, that's going to be 1 times 2, so minus 2. And it gives us the 2, 1 state, right? So we have root 4, we have 2, H bar 2, 1 is that the state that's down here, which, we know that's the next state in that manifold. What is it equal to? Well, we just take that J1, 1 minus, right here, J1 minus plus J2 minus, operating on this 1, 1, 1, 1 state. And what do we get? Well, we get J1 minus operating on 1, 1, 1, 1, and J2 minus operating on 1, 1, 1, 1. This is going to be equal to H bar square root of 1 plus 1 times 1, that's square root 2, times 1, 1, 0, 1. And we likewise for the J2 minus, they have the same quantum numbers, so root 2, 1, 1, 1, 0 state, right? So what does this mean? Well, bring the 2 H bar over. and we get 2, 1 state is equal to h1, the h bars cancel, over root 2, 1, 1, 1, 0, 1 plus 1, 1, 1, 0 state, right? So the lower state in that manifold is figured out that way. 1, 1, 1, 0 plus 1, 1, 0, 1. And then we do it again. What's the lowering operator on that give us, right? And we just take that j minus operating on to 1 again. And what does that one give us? Well, if we go through all of these, the action on it, well, j is still, this is going to give us h bar square root 2, this is still 6, right? And it's going to be minus, well, that's going to be 0, right? 1 minus 1 is 0. And that gives us 2, 0 as our ket quantum numbers, right? In terms of figuring out the other, in terms of the other side, we have j1 minus plus j2 minus operating on 1 over root 2, 1, 1, 0, 1 plus 1, 1, 1, 0, right? And then you take this and operate on both of these, and then you take this and operate on both of these again. And again, you know, just by using how that lowering operator works, this ends up, you know, I'm not going to go through all of the gory details on this, but what this shows us is what you end up with is this 2, 0 state ends up being equal to 1 over root 6 times 1, 1, 1, negative 1, plus 2, 1, 1, 0, 0, plus 1, 1, negative 1, 1, like that. And now we've figured out this 2, 0 state. And hopefully you can see that this gets a little time consuming and probably not the way you want to spend a weekend. But we have a process that can get us through figuring out how to add all these angular momentum together. We repeat this 2 more times, and we get everything in this manifold. We get the 2, negative 1 state, and that ends up being 1 over root 2 times 1, 1, 0, negative 1, plus 1, 1, negative 1, 0. And then the 2, negative 2 state ends up being just the 1, 1, negative 1, negative 1 state at the bottom. So we've got these 1, 2, 3, 4, 5 different states in our manifold. Unfortunately, there are 9 states in this, right? There's 2j plus 1 times 2j plus 1 states, so we have 9 different states. We then, you know, have to apply orthogonality. We'll look at this state to get to the next manifold. We know that the 2, 1 state there has to be orthogonal to the 1, 1 state at the top of the next manifold. So we just take that to 1, 1, 1 inner product, set it equal to 0, but we write this 1, 1 state in terms of a linear combination of all our uncoupled basis states. The only ones that are going to matter are the ones that are in the 2, 1 state. All the other ones are just going to be orthogonal to these two. So we can just write this as A 1, 1, 1, 0 plus B 1, 1, 0, 1. And then this inner product ends up being 1 over root 2, 1, 1, 1, 0 plus 1, 1, 0, 1. Inner product with A 1, 1, 1, 0 plus B 1, 1, 0, 1, like that. And this gives us A over root 2 plus B over root 2. And this inner product has to be 0 because they're orthogonal, which tells us A is equal to negative B, or our 1, 1 state is going to be equal to, after normalization, we need that 1 over root 2 there, but it's going to be equal to 1, 1, 1, 0 minus 1, 1, 0, 1. And now we have the top state in that next manifold, and we can go down through that manifold and figure out the states, the 3 states in that, the 1, 1, the 1, 1, the 1, 0, and then going down again, we'll get the 1, negative 1 state. Then we use orthogonality again on that state to get our 0, 0 state. And you can hopefully see that's our general process for figuring out all these states. There are 9 of them. That was just with the 2 spin equal 1 states. You can see how this would get sort of more complicated and more tedious as it goes on. Thankfully, it doesn't really change. You know, you have 2 spin 1/2 systems. They add together to have the same possible total angular momentum states. Likewise, a spin 1 and a spin 1/2 system put together, the angular momentum are always going to add to the same sort of coupled versus uncoupled basis states, right? And in general, we can just sort of look up these what are called Clebsch-Gordan's coefficients. If you think about what we're really doing here, what we're showing is we have, consider this example. What we've done is we've written a JM state in terms of a linear combination of our uncoupled bases. So what we're doing is we're figuring out all the JM states in terms of a linear combination of the possible, M1 is equal to negative J1 to J1, M2 is equal to negative J2 all the way up to J2. We're figuring out how to write this in terms of those things. So we're using sort of the completeness relation of our J1, J2, M1, M2, J1, J2, M1, M2. We can write that JM state as a linear combination of our uncoupled basis states using that completeness relationship, where this completeness or closure tells us that's essentially just the identity matrix. We're projecting it onto all those basis states, which, if we bring this in, gives us M1 is equal to negative J1, J1, M2 is equal to negative J2, J2. We end up with this J1, J2, M1, M2, JM, J1, J2, M1, M2. We're figuring out, all we did up there is essentially figure out these coefficients in this expansion, right? So these are, you can look these up. These are what we call Clebsch-Gordan coefficients. They can, in general, you can write them just as these scalars, where we have some M1 is equal to negative J1 to J1, M2 is equal to negative J2 to J2. These Clebsch-Gordan coefficients, J1, J2, J, M1, M2, M, J1, J2, M1, M2. And you can essentially just look up these coefficients in a table. And, thankfully these calculations have been done. I like to think of it as, if you think way back to when we had to figure out moments of inertia in classical mechanics and intro mechanics, you had to integrate over all these shapes and densities to figure it out. We needed to know how to do that. But in general, for standard shapes and that, you could just look up the moments of inertia in a table. It's the same with this. We want to know the process of how to get these coefficients and how and why it works. But ultimately, when it's said and done, if I have, say a two-spin system where the first system has, a spin of 2, and the second one has, say, 5/2 total angular momentum, and I want to add them together, it could take, if I'm honest, probably hours for me to figure out all of these by hand from scratch. I'm just going to look up in a table the Clebsch-Gordon coefficients for that type of system when I'm adding a angular momentum of 2 and angular momentum of 5/2 system together, and I'll have answered all of those things. So, for example, this spin one sort of system we just did, if I look up, in McIntyre, they list the tables for the spin 1-1 systems. So I have two systems where the first system's got a spin of 1, the second system has a spin of 1. I want to look at my coupled bases, and I want to know, okay, how do I write the 2-1 system in terms of my uncoupled bases? Well, I have 1 over root 2, the 1-0 state, and a 1 over root 2 in the 1-0 state, and that's how I make it up. And if you look up here with what we first did, over here on the left, that's what we got. The 1-0 and the 0-1, the 1-0 and 0-1 state is our 2-1 state. So our 2-1 state is our 1 over root 2, the 1-0 state, and 1 over root 2, the 0-1 state. So right there, that's our 1-0 state times the 1 over root 2, and our 0-1 state times the 1 over root 2. And you can look up, 1 over root 6 and 1 over root, all of this one right here. What is my 2-0 state in that what is that 2-0 state? It's going to be 1 over root 6, 2 over root 3, 1 over root 6 for the 3 states that we got there. So you can see how we can just sort of pick off on the table how these states relate to each other rather than doing all of the calculations we just did. We still need to know how to make those calculations, but in general, we can just walk through that. And then it has, this is the J equals 2 manifold is this first part of the table, the J equals 1 manifold, and then the J equals 0 manifold. And you can pick these values off the table. So we'll get used to using these, how to make them, like that process again, in our synchronous sessions and through the homework in that. If you have questions on how we're doing all this, please email me, bring them up in the synchronous sessions. We'll discuss this a lot more and go from there. But that's generally how we can add angular momentum in quantum mechanics. I will see you in our synchronous sessions.